Okay, good day. Um, this is AP Calculus. I am Mr. McCully, and this is our presentation for section 5.4. And so today we will be talking about developing properties for the natural, excuse me, natural exponential function. We're going to be differentiating natural exponential functions and integrating the natural exponential function. So first thing we want to talk about is the derivative of the natural exponential function. And as you can see, they have two basic ones that talk about e to the x. And the derivative of e to the x is going to be equal to e to the x. And I know that's a surprising result. We'll talk about why that is in a moment. And then here we have a instance of the chain rule. So if you have some e to another function u, and u being defined in x, it's going to be e. The derivative of that will be e to the u times the derivative of whatever that u is. And so if I want to talk about the proof of that, the way I'm going to talk about the proof of that is I'm going to talk about the fact that or a fact that we already know, is we already know that the ln of e to the x is equal to x. And that's actually an Algebra 2 concept that we talked about a couple years ago. And here's what we're going to do. We're going to try and do the derivative of that thing. And if you remember, the derivative of anything ln of u is 1 over that um, that u, so e to the x, times the derivative d over dx of whatever that thing is. It's a chain instance of the chain rule. And then we remember that the derivative of x is just 1. And so if I try and move this expression to the other side, I'm going to multiply both sides by e to the x times e to the x. These cancel, and I'm left with the derivative with respect to x of whatever e to the x is just e to the x. I know that's kind of an odd result, but that's the way it works out. So the integration rules are very similar. The integral of e to the x is e to the x, and the integral of e to the u du is e to the u plus some constant c. So pretty straightforward stuff. Now, this particular section does a lot with the excuse me, natural exponential function. And some of the beginning questions are kind of review. So I thought I'd start with a real simple review question talking about exponential functions. And number 8, it says this. It goes 200 e to the negative 4x is equal to 15. All right, so we're trying, the directions tell us to solve for x. Okay, come on, Macaulay. All right, so we're solving for x, and so the first thing I want to do is I want to get this expression e to the negative 4x by itself, so I'm going to divide both sides by 200, so I have e to the negative 4x is equal to 15 over 200, and if you remember from the proof that we just did, is that the ln of e to the x is just equal to x, or if you remember the property from last year where if you have the ln of e of anything a to the x, that's the same as a ln of, oops, I screwed that up too, man, I'm winning today. All right, so I said if you took the ln of x to the a, that's going to be equal to a ln of x, whatever that might be. So here's what I'm going to do. I'm going to take the ln of both sides, and then what I can do is I can bring this down. I can bring that down in front, and that'll give me negative 4x times the ln of e, which we know to be just 1, equals the ln of 15 over 200. Divide both sides by negative 4, divide by negative 4, and we've got x equals this expression, and that you're just going to grab a calculator for. So you go the ln of 15 divided by 200 and parenthesis divided by -4, and we get 0.648. So we'll call it 0.648. So if you took e to the -4 times 0.648, and again, when you multiply by negative, it's going to be 1 divided by times 200, you get 15. And that makes sense because we obviously need this to be a division. And so when we make it negative, it'll be 1 over some value to the e. So that is our solution, and that makes pretty good sense. So I'm pretty happy with that. All right, now let's get on to derivatives. Let's start with a simple one to begin with, and they want us to do the derivative of y equals e to the 5x. Actually, I think it's negative 5x. So we are deriving with respect to x. And again, since we are doing the derivative, this is not just x, it is an expression in terms of x. So this is a chain rule property. So when we go to do the derivative of y with respect to x is going to be just that e to the negative 5x times the derivative of that expression, which in this case, the derivative of negative 5x is negative 5. So my final answer for dy over dx or y prime, whichever you prefer, is going to be negative 5e to the negative 5x. All right, moving on. Let's look at a little bit more challenging one. Let's look at, what do I have there? Number 46. In number 46, they say y equals x e to the x. And here I see a product of x and e to the x. So remembering the product rule, so if you have f of x is equal to g of x, h of x, then the first derivative of that thing will be g of x times h prime of x plus g prime of x, h of x. So that's what we're going to do there. So when we go to do the derivative of this thing, with respect to x, I'm going to have dy over dx is equal to x times the derivative of that. Remember, the derivative of e to the x is just e to the x plus the derivative of the first term, so the derivative of x is just 1. And then I leave the second one alone, so e to the x. So my final answer for this one, e to the x plus e to the x. And you know, the book may factor that e to the x out, but you don't have to. And that is our solution. All right. Moving quickly along. Excuse me. 52. And this one is a skosh more challenging. So y equals the ln of the expression 1 plus e to the x over 1 minus e to the x. And so I'm going to use that property of logarithms and do it right this time, where I say it's the ln of 1 plus e to the x, and then it's minus ln of 1 minus e to the x. And so doing the derivative, and again, we have a composition of functions. We have ln of some function here, and then minus the ln of another function. So we have to use the chain rule version of the ln derivative rule. And so I'm deriving with respect to x. So dy over dx is going to be 1 over the inside expression, 1 plus e to the x, times the derivative of what's on the outside. And what's on the outside, or inside, excuse me, what's on the inside is 1 plus e to the x, and so the derivative of a constant is just 0. And then the derivative of e to the x is e to the x. And then from that, I'm going to subtract. And again, I have an ln rule here. So 1 over the inside function, so 1 minus e to the x, times the derivative of that inside function. And the derivative of 1 is 0, and the derivative of negative e to the x is negative e to the x. And so I finish this thing out by saying it is 1 over 1 plus e to the x, and then minus a negative is going to be like plus a positive. 1, or excuse me, Oh, they made a little mistake here. Notice I need to multiply these two together. So let's do that right. 1 times e to the x is going to be e to the x, and that's over 1 plus e to the x. And then minus a negative is going to be a positive, and then we'll say it's e to the x over 1 minus e to the x. Now, we could simplify this a little bit and find common denominator and make it one fraction, but that's not necessary for our particular problems here. So we'll leave that as our final answer. That's fine. All right, my final one for the day is number 70. And it is e to the xy plus x squared plus y squared is equal to 10. So this one says derive implicitly, and we need to review that. We haven't done them for a while, so I'm going to start sticking some of those in, and it is in one of the homework problems. So we want to do the implicit differentiation of this one, and this one poses a few challenges. We have it's e, the u that is the power of e is a product, so we're going to have a product rule when we go to divide this. And then these two are fairly simple, and the derivative constant is always 0. So let's get started here. Taking the derivative of the first one, I'm going to have e to the x plus, or xy, not x plus y, just xy. And that's, so derivative of that times the derivative of this expression. So we have x times whatever the derivative of y is, plus the derivative of x is just 1 times y. And then that completes the derivative of this expression. And to that, we need to add the derivative of x squared, which is 2x. And then to that, we needed to add the derivative of y squared, which will be 2y times the derivative of whatever y is with respect to x. And then we have the derivative of 10 is 0. So they want us to solve for just dy. So here's what I'm going to have to do. I'm going to have to distribute this e to the xy to both terms. So I'm going to have x e to the xy dy over dx plus y e to the xy plus 2x plus 2y dy over dx equal to 0. So now I see 1, 2, 3, 4 terms. 2 of them have dy over dx, so I'm going to leave those on the left-hand side. And then I'm going to move the other 2 to the other side. So on the left-hand side, I'm left with e, or x e to the xy dy over dx plus 2y dy over dx. And then I have to move this one to the right and this one to the right through a subtraction. So I have negative y e to the xy. And then it's also going to be I screwed it up, y e to the xy, and then a minus 2x. And so from this left-hand side here, I'm going to factor out a dy over dx. So I have dy over dx, that's a d, times the quantity x e to the xy plus 2y, and that's still going to be equal to this quantity, so negative y e to the xy minus 2x, and then I'm going to divide both sides by this expression here on the left. So my final answer, dy over dx, unless I can simplify it, I don't think that we're going to be able to, is going to be equal to negative y e to the xy minus 2x all over x e to the xy plus 2y. And that is my final solution for that particular problem. Okay. I'm recording this on a snow day Friday, and it's looking like we may have another snow day on Monday. For those of you who are watching this, please, please, please feel free to use the email address that I gave you to ask questions or leave comments in the comment section below. Hope you have a good day off. This is a pretty short one. It only ends up being 15 minutes. So have a good day. Goodbye.